Today I will talk about this project that we just started today. The result you can see is quite just came out of the model 2 days ago, so I put it together now and I present it with an interesting idea, so I wanted to share. And might not be the best example after being coming presenting because I'm using efficiency. But I'm looking forward if you can change it. I think you know some problems before we had for this kind of data I'm gonna introduce. So then this project called POLLENOMICS, and we are trying to look at the farming history in Europe and how much human actually affect the land use, land cover, therefore like changing the forest into the cities, into the farmland, or into like deforestation to use the forest. It's a multidisciplinary collaboration between different peoples, and we are working together with Aaron, who has the DNA data from the biology department, and Nikolska from National Department of Physical Geography and Ecosystem, who is working with climate models and vegetation dynamic models, who can use the result of this data, and we can somehow evaluate if this result we get is close to what we expect. And then also Johan, who was my PhD supervisor here in Metastat. Just some quick motivation, why do we do this and why do we need these things, is that, as I already a bit mentioned, this here we can see the climate models with different parts of it, with different cycles, atmospheric cycle, we have water cycles, and as you see, the land use and land cover is a part of this big picture. So in order that we can get a climate models that can predict good in the values, we need to have different part of this system with the least uncertainty possible. And there are factors that can add to this uncertainty from different parts of these cycles. And here we're mainly looking at the land use and agricultural and human land use to see the effect of human in the climate and the climate change. So what has been done so far, there are different scenarios that estimate the human land use in time, and this can go from today back 10,000 years ago or even more. And many of these scenarios, on the first row you can see the height scenario. It's a history database of database, and then the second one is Kaplan model. And these two both working with the human population, and when they go back in time, they have to do lots of estimation of how much population where. And then, for example, Kaplan also take into account the technology advancement, but like HIVE doesn't do that. Recent HIVE is looking at the archaeological data to see to get a better estimate of the human population and how much they were affecting the land. So you can see in the first row and the second row already go back in time. There are 5 different time frames here. They get quite different from each other. And that's, for example, one big uncertainty in this field, that which one is true, which one we should use in the climate model, and how do we know actually which one is correct. So what we want to do now is that we want to use 2 sorts of data. There are proxy-based, so there are pollen-based vegetation, and there are DNA from the human. And based on those 2 proxy-based, we want to reconstruct this human land use. The first row showing you the pollen data that we have in their source. The last row showing the DNA data and how human has used involved, but then we are here looking at the European one, and we want to combine them to inform us about the human and interaction with the land. So more specifically, if you look at the pollen-based data, you can see that this is from today, go back 10,000, and there are time frame that we are looking at. So it's like a recent in common era, there are usually 500 less than 500 year difference. After that, there are 500 year intervals between the time frame. So these pollen data, they are collected from the lake and dogs, and so they go take a sediment out, the bioecologists, and count the number of pollen in these things, and then based on the pollen production and the dispersion rates they have, they can estimate what was the vegetation around the lake. And as you can see, they are quite sparse because we don't have lake everywhere. So then we need to come with a model that can interpolate this data. So these data are in compositional form, and you have, it's like each of the land cover type. For example, we are looking at the coniferous forest, broadleaf forest, and unforested land, which is a combination of the open, natural openness and human land use. They are all between 0 and 1, the proportions, and they sum to 1. So when we are working with them to model them, we should take this into account. So here, and it's trying to say that just doing a simple linear regression doesn't work because we cannot guarantee the prediction E in the interval 0 to 1. And therefore, we need some kind of transformation in the compositional space. And we are using ALR's transport information, and it's helping us because it reduces dimensionality also. So I'm trying to predict 3 different land cover, so that from those I can also estimate the human land use using the ALR. Going from 3, 4 fields, we go to 1 less field. So we go either to 3 or 2 fields. So it also has the computational aspect of estimating the latent field and the land covers. So this is our DNA data. You can see that it's all around the world, and the amount is vary. I can hopefully show you this one. So this data has been produced by my colleague Aaron, and that show that going back going from the back in time to these days, how human has moved. I can zoom hopefully. Yeah. So this is how Europe and movement of human look like based on this DNA data. I'm trying to go to Scandinavia area so that you can see better. So we try to use now this data. We have a starting point of where the DNA sampled and dated and where they are in different times. So then we can use this information. Let's hope that I don't mess up with your Zoom. There.
Wait a minute.
Okay. And then if I combine them, because for this conference and the first study, we are looking at Europe, so we are just looking at the area above Africa and then up to Caspian Sea. So this is how the combination of data look like. So in this case, we have the point of the DNA, where they are, the location of them, and then we have the grid of the compositional pollen data of the 3 different types that we're going to combine together to get an understanding of the human land use. So to do this, we are in general, we have 25 time frames. Here I'm looking at 10, and then we are doing a hierarchical Bayesian model, and for inference and using an MCMC, which is also taking for compositional data and taking into account the point process as well. So this is the hierarchical model Bayesian setup that I have. Different part of it. On the top row, you see the parameters that the hyperparameters that we have. The blue ones are the parameters that I need to estimate in the model. We then have a latent field of X that includes the 2 land cover type and 1 human land use, so that 3 of them together can base my pollen reconstruction, which is a distribution, and the other side of it, the latent field for the human land use go directly to the DNA data through a low Gaussian process, which is for the clone process in this case. So if you look at the model, I have the plot here, so that if you want to remember compare, it's this type of model. We do a lot of transformation to first pick this 0 and 1 property, and also how to incorporate the human land use parts that we get from DNA into the pollen and other way around, so that we get informed from both of the data sources that we have. And that is going through this through the H function, which is the combination of those probability that I get for different fields. And the inference, we are using the two-block MCMC algorithm. For the first block, we are updating the alpha parameter for my compositional data or replay distribution, and data for my covariance that I can use in this model, and my fields, latent fields that I have. And for that, we are using a model algorithm, which is adaptive metropolis adjusted Lagrange mean. And for the kappa and rho, which are the parameter for my Gaussian Markov random field, we are using a random walk for the kappa and a coordinate posterior for rho. And this is all to help us to get it computationally good enough that we can run it. So we come up with different things here so that it can be fast and so that it is efficient. The whole samples for one time frame take 4 hours. I don't know how much Lina would take. It's around 3,240 grids and 4 different fields. So that it's still okay, but it takes some time. So a bit deeper into this different setup that we do and why we do it. The good property with model, we do this proposal and the equation up there that has 2 different parts. One is the expected Fisher information, which I denoted with the I, and that it becomes second expected value of the second derivative of my log likelihood. And for the Gaussian field, Gaussian Markov random field, this becomes the sparse matrix of Q, which is then good because it's sparse and it's fast for computation and inversion. And also in this way, we get information about in each setup, we get informed which direction to go and which step we take so that we kind of speed up the MCMC. And there is a parameter epsilon that is a step size of the model that we can adapt it, tune it so that we get enough acceptance rate, which here is 57%. So this together help us to be fast and efficient in the computation part of these big fields that we have. Then for the kappa and rho, we are doing some combination of the conjugate, which is helpful always to get the closed form of the distribution so we can directly sample from, and that's we are using here for it. And so we can integrate out, for example, the rho from the posterior of the kappa, and then we have a closed form to sample directly from, and also for the rho we have a closed form so we can directly sample from. And then for each step of this kappa that we want to update, we are just doing the logarithmic random walk, and then when we have the proposal, we just use that in the closed form of the rho that we find. So this way, it's also the computation gets fast. So we do all these things, and then we are in the Bayesian conference, so I thought maybe I should talk a little bit prior. There have been so many thoughts behind what to do and what to expect. And of course, we have a couple of papers and all the reviewers asking why this, why that. So we come up with this. We're using generally a weight prior for alpha, for example, a gamma. That's the simplest one here in this page. And then for covariance beta, because we have a compositional fields that they are related to each other, we cannot drop one of the polarity for one field and keep it for others. So we have to have everything, but the effect of them are different. So it's in like a linear model, we can see if it's a polarity is not, if the one polarity is not significant, drop it. Here, it might be significant for one of the composition, not the other. So then we come up with this horseshoe priors that what it does, it shrinks towards zero, where the polarity is not for one of the field, and then it can still have some value for the other fields. So that also helps in selection for us. Then we use a conjugate inverse Wishart, which is help us to have this nice Wishart closed form distribution. And then for kappa, we are using another aspect here because kappa is taking the range of it's inverse of the range of the field. So we have some idea of what are the lowest amount it can be. So we are using the probability that that range cannot be less than 1 because the grid we have are 1. And then we come up with this number, which a good prior to start with. And so all these things I've done 4 hours multiple 10 times estimation of different things. Here, or you can see all the fields, and for reference, you can see Europe boundary, but I mean, of course, like many years, like 6,000 years ago, there were no boundaries, so just for reference for your eyes, that you know where to look. This is the result we get. So the first row show the coniferous forest in Europe, second one show the map of broadleaf forest, and last one show the map of unforested land. So in this here, the unforested land is a combination of the human and openness. So like haven't deep into it yet, but some like knowledge, if we kind of think about it, is like broadleaf forests are a bit higher in this part of Europe, which just makes sense. When we go north, it gets more of a coniferous forest. So then the first row should have a darker color on the north and on the around the Alps area, which we can see this pattern. And then if we go a bit more further and look at actually the 4 different maps that we were looking for. So then we have coniferous forest, the first row, broadleaf forest, unforested land, which is now representative of the open natural openness. And the last one is the human land use. That it shows that where human were doing agriculture back in time, and this is around 3,500, go back to 5,500 years ago. This I have to yet check with my colleagues who are more experts to make sure that the result is makes sense at least. So saying that. It's a lot of things to do with this project, but I just wanted to show and present it that we can combine different sorts of data with different modalities. Some one is point process, one is compositional, and one deeply grid. And we can combine the model, which we at the first it will be quite complicated, but it's possible to get the result. Some part of this work has been already published, so we have already published the part where we are producing the land cover, and that has been set up. This part of the point process we are adding now is a new part that we are working with. And things to evaluate, of course, is how these maps look like. And one thing we can do, for example, we can compare it to the dynamic vegetation models, which they just reduce the vegetation type based on the climate models. And then also, for example, one thing we can do is to compare the human land use that we get with the already new scenario to see where this result with DNA look like, where they end up in this source of the data that we can get. Another idea for this data is that, which we're kind of excited about, is we want to look at how this we could see it already in the DNA data. We can see how the human move. So we want to do a similar thing with the pollen data to see if we can find the probability maps that can identify how pollen data spread in Europe or in different direction. And then based on that, if you can see that if the human land use part of the pollen data have a similar pattern with the DNA data movement or not, so that we can derive some conclusion on this, that it is actually human has affected the land or not. I think this is my last picture. Yeah, that's even two big references that I'm using. There are a bunch of others, but I just use these two because one of them is the compositional and the second one is the Gaussian, low Gaussian flux process. Thank you.